In this video, we are going to be covering the topics in chapter 15, which have to do with nuclear magnetic resonance spectroscopy. Notice that these topics are discussed in a different chapter if you're utilizing the second edition for the organic chemistry textbook from David Klein. NMR is the abbreviation that stands for nuclear magnetic resonance spectroscopy. This may be the most powerful method in order to gain structural information about organic compounds. And it is the one that we first used as organic chemists in order to get insight into the structure of a particular molecule. NMR involves the interaction between electromagnetic radiation, a specific type of light, and the nucleus of an atom. In this chapter, we are going to be focusing on carbon and hydrogen because those are common nuclei that can be found in many organic compounds. One thing that we need to focus on throughout this chapter is that the structure of a molecule, meaning what atoms are going to be interacting with the nuclei that we are interested in, are going to be affecting how the radiation that is utilized in this process interacts with the nucleus itself in the context of a molecule. When it comes to atoms, in general chemistry, you guys learned that there are subatomic particles that are present in atoms. Those include protons, neutrons, and electrons. And we are going to be talking about in this chapter how these subatomic particles are going to be involved in this type of spectroscopy. First, we must establish that protons and neutrons, which are the subatomic particles that live in the nucleus of an atom, behave as if they were spinning. One of the parameters that it is necessary in order for NMR to work is that the particular atom that we're interested in must have an odd number of protons and or an odd number of neutrons. The reason is because if an atom has these parameters, it will have a net nuclear spin. That's why when it comes to NMR, we can actually study the NMR of protons, as you can see, given by the designation H1. We can study carbon-13, which are the two that we're going to be focusing on in this chapter. But in addition, you can do NMR spectroscopy for nitrogen-15, fluorine-19, and even phosphorus-31. One of the things that we also have to consider is that the spinning charge in the nucleus is going to create a magnetic moment. From physics, you know that if you have a moving charge, it's going to be creating its own magnetic field. And that's what we see in these atoms. Okay? So again, magnetic moment, magnetic field, they are synonyms of each other. Understand that if you have a spinning charge, specifically, you're going to have a magnetic field that is going to be created, and it is actually existing perpendicular to the axis of a nuclear spin. So, as you can see illustrated in the bottom of the slide, this is illustrating how if you have the rotation because of your moving charge in the nucleus, what kind of magnetic field is created, and that is designed or designated by the dotted arrows. Now, when it comes to these magnetic fields that are created by these moving charges that are present in the nucleus, understand that at first these magnetic fields are going to be random, which is what we see illustrated in figure A. Now, if these disordered magnetic fields that are present in the atoms are then exposed to an external magnetic field, which is designated by B0, that B0, designation, then they are going to adopt one of two arrangements. They are either going to go and align with the applied external field, or they're going to be they're going to be going against that applied external field. Let's now define what we call these different spin states that are created from the application into our atoms of an external applied magnetic field. So we're going to have two spin states. We're going to have the beta spin state, which, as you can see, it opposes the external applied field, and they're going to be higher in energy. Those I'm going to be highlighting in orange. As you can see, in the figure that we have in the top, is just illustrating the energy difference between the different spin states. In the figure that we have in the bottom, it actually illustrates how the beta spin state is against the applied magnetic field. Now, I'm going to highlight in green the alpha spin state. And then the alpha spin state, which, as you can see, is aligned in the same direction of the applied magnetic field, is lower in energy. Okay? The analogy that we can rationalize why the beta spin state is higher in energy than the alpha spin state is kind of like if you think about swimming with a current or swimming against a current. Beta spin state will be kind of like swimming against the current, so it will take more energy. That's why it's higher energy, in terms of the analogy. And the alpha spin state is going to be kind of like if we are trying to think of the energy that we will spend if we're swimming with the current. Again, because you're going with the current, then that means that it's going to take less energy. Just a little analogy that will help you think about it. But in summary, the magnetic field that are created by the spinning charges in the nucleus will align either with the external field or against this external field. Now, understand when specifically an atom, okay, that has an alpha spin state is exposed to radio waves, because I already established that electromagnetic radiation, it is necessary in the process of utilizing this NMR spectroscopy. So when radio waves are exposed to an atom, then the alpha spin state is going to flip into the beta spin state. Because once it is exposed to these radio waves or these radio frequencies, photons are going to be are going to be absorbed, and then that's going to create the conversion of the alpha spin state into the beta spin state. So you can imagine now that in this process, our alpha spin state is going to be converted into higher energy. And then once it is in that higher energy, it's actually going to relax back into the ground state. And because it goes back and forth from alpha to beta and then relaxing back to alpha, that whole process is called resonance. One of the things that we need to establish is that understand that the stronger the magnetic field that it is in this system, the greater the energy gap that is going to be present between the alpha spin state and the beta spin state. So far, we have only talked about the moving charges that are present in the nucleus. But let's remind ourselves that in these atoms, we also have electrons. And having an applied magnetic field into electrons, which are also charged particles, will have the creation of others magnetic fields. But now these are going to be specifically coming from the electrons. So when we observe what happens to these atoms at the level of now taking into consideration what's happening to the electrons, remember, the electrons are going to be circling the nucleus. And in the figure that we have right here, again, the proton, which is going to be the charged particle that lives in the nucleus, once you have the applied external field, B naught, remember that it's going to create an induced magnetic field. Now, in addition to it, remember that there's going to be electrons that are circling that nucleus. And I just decided to write a few of them here. Now, this applied external field is going to cause the electrons to circulate and induce an opposing magnetic field, which is just called the process of diamagnetism. And because now the electrons are also going to create a magnetic field, then we can view our nucleus as being shielded by those electrons or de-shielded by those electrons. So let's study the concepts of shielding and de-shielding a little bit more in depth. So remember, the concepts of shielded or de-shielded come from electrons creating a magnetic field because they have that external magnetic field applied to them. Okay? So, if we look at the nucleus, and that nucleus is surrounded by a great amount of electron density, then what happens is that because we have a great amount of electron density, that nucleus will experience a lesser extent of that external applied magnetic field. Okay, so that's what we mean with a nucleus being shielded. If the nucleus, on the other hand, is surrounded by less electron density, it will experience an external magnetic field, that B naught, to a greater extent. And what that means is that we call that nucleus as being de-shielded. Okay? Now, understand that these different electronic environments will allow us to see different signals when we laser focus, in particular, studying NMR. In this class, we are going to be focusing on proton NMR and carbon NMR. So understand that the presence of this electron shielding or de-shielding the nucleus, we're going to see its effect specifically in the spectrum when we are running an NMR. Let's look now at an example of how this occurs. So this specifically is a proton NMR. And in this proton NMR, as you can see, we have specifically a proton NMR for a particular molecule. This is an ester. And in a proton NMR, we are laser focusing on the nucleus of the proton of H1. Now, understand that there are some concepts that I want to introduce now and are going to come up throughout the discussion for chapter 15. Whenever we have a specific area that is closer to zero in our NMR spectrum, that is called upfield. If we're moving from zero toward larger values, that is called downfield. Okay? Now let's observe what we have, particularly in the following example. As you can see here, outlined in different colors, we have different hydrogens. And again, at this time, we are not even addressing how are these hydrogens placed here. We're just understanding why are some things more downfield and why are some things more upfield, okay? So I just want to talk about the extreme. Things that are upfield and things that are downfield. And I want to explain the reasoning in terms of electron density of why we have these observations. So what I want to do now specifically is to focus on the red protons, which as you can see are going to be more downfield. And I want to also focus on the blue protons, which as you can see are going to be more upfield. And I want to discuss why is it that we see in this position in the spectrum. So, as you can see in this figure, it is illustrating that those protons that are sitting on that carbon that are labeled red are shown downfield compared to the other signals that we have in the NMR spectrum, okay? So, protons that are said to be de-shielded, okay, are said to be more downfield because remember, when you are de-shielded, you're going to feel that external magnetic field to a greater extent, okay? So it is said that they are going to be in higher frequency. Now, understand that this nucleus that it is de-shielded, if we rationalize why is it that it's de-shielded, notice that these protons, and I'm going to highlight it also in red, are sitting next to an atom that is electronegative, meaning that oxygen. So because the carbon where those hydrogens are sitting is actually attached to an electronegative atom. Remember that when it comes to electronegativity, that oxygen is going to pull electron density towards itself because it's more electronegative than carbon. When that occurs, that means that the electron density around that proton is less. If that electron density is less, then that means that that proton is going to be more de-shielded, and the effect that we see in the NMR is that we're going to see a more downfield. Now, let's talk about the protons that are next door. As you can see, the protons that are on the carbon next door are not directly attached. So the carbon atom where those protons are sitting is not directly attached to the oxygen atom. It's just removed several bonds away. So those protons are not going to be receiving as much that effect of that electronegative atom. So in the context of this molecule, those protons in blue are more shielded, meaning they're going to have a greater electron density around them. And when that happens, we consider that to be lower frequency, and that's why it shows up more upfield in our proton NMR. And again, when it comes to upfield, downfield, those terminologies actually had to do with chemical shift, which we will have an in-depth discussion about that topic throughout the discussions in this chapter. So, to summarize what we are giving in this introduction, remember the amount of radio wave energy necessary for taking an alpha spin state to the beta spin state, okay, depends on the electronic environment of the atom. As I mentioned previously, when we have that alpha spin state flip to the beta spin state, okay, remember that we're going to be absorbing some photons from that radio wave. And when that flip happens, remember, once they are excited, they have to go back to ground state. And because of that flip between alpha and beta during that process, that's what is known as resonance. That's the resonance part of nuclear magnetic resonance. Okay. Now, understand that this term resonance, again, is specifically from flipping from the alpha state to the beta state. It is not related to the topics that you guys talked about previously when it comes to electrons and molecular orbitals and them being in resonance, just because there are going to be some areas of the molecule that there are some molecular orbitals that can be filled. So it doesn't have to do with that. So I just wanted to clarify that. Now, lastly, understand that the amount of energy required for each proton, so you will see me or hear me calling this a proton often in these videos. So the amount of energy required for each proton for its spin to flip, it actually tells us about the electronic environment in which it's at. And that is the basis of how we are going to be observing in this chapter, how we observe the structural information for a particular compound.